Right, so let's welcome back Asilata for day 3 of triangulations, etc.
Thank you. I hope Hawaii can hear me. I'm assuming they can. Maybe that's not the right assumption, but yep, I see some nodding heads. Great. Great. So thank you everyone for coming back once again. So today I want to discuss PPTs once again, pointed pseudo triangulations. And yesterday we talked quite a bit about like how to define them for generic configurations. I said mumbled some stuff about non-generic configurations. I'll actually leave it at that. More about that stuff is in the notes, so you can play around with it. It's actually really fun, and I don't know much about it at all, so have fun with that. But today I want to say something about like, okay, I defined this thing, pseudo triangles, pseudo triangulations, blah, blah, blah. How do they actually show up in anything that's connected to anything else? And so there are two kind of ways in which they naturally show up, and I want to discuss them both. So one is rigid motions, which is part of the etc. in the course. And the second one is arcs in a configuration. But let's talk about rigid motions first. And in the interest of getting to more of the representation theory in the last 2 days of the course, I won't give too many proofs of this stuff. It's just like the stuff from yesterday. It's all elementary. It's only linear algebra, but it's not easy. So beware, okay? But anyway, let's see what we're doing. So let's talk about rigid motions. So let me make a couple of definitions. So one thing that we'll be dealing with when we discuss rigid motions are frameworks. So a framework, and I hinted at this yesterday. I mean, if we have a graph in the plane, drawn using planar graph drawn using straight lines, I can alternately think of it as kind of being constructed out of rigid rods. And so a framework G with vertices, so a vertex set maybe, and an edge set consists of, so it's basically points in the plane okay, distinct points in the plane, and the edges are thought of as straight lines joining PI and PJ, and you should think of them really as a straight line rod. Okay, so where IJ is the straight line, line segment maybe. Okay, and thought of as a rigid rod. Meaning in anything we do with frameworks, when we move points around, we're not allowed to shrink or extend the length of IJ, the edge IJ, okay? So, I mean, an example is just, some. And I don't think this is part of the definition, but typically, okay, typically these will be non-crossing. So unless I say otherwise, edges in my framework shouldn't cross. Okay, so I have some planar graph like this. And now what I want to think about these frameworks is that each vertex is kind of a hinge, and each rod is moving around that hinge. And I want to move the points around in the plane so that I don't change the length of the rods. I can change any other lengths, of course. Okay, so you might think, this framework, for example, can kind of wiggle around it has three kind of dangling edges, and you can dangle them around. And of course, every framework can be, I mean, any isometry of the plane can be applied to any framework, and so that's allowed. Okay, so you can translate around the whole thing or rotate the whole thing. So let's define a rigid motion. A rigid motion of a framework G is exactly what you think it is a continuous function, I think. So what do I want? I want a function that wiggles my points. Okay, so maybe in some epsilon neighborhood. So at time 0, I want my function to output the positions of the points in my framework. And at other times, it's wiggling the framework as long as it doesn't change the length. So what does this function need to satisfy such that, first of all, pi of 0 is pi for all I. Okay, and secondly, if I take, so for all edges, if I look at pi of t minus pj of t, this segment has length equal to the original length. Okay, so that's all that I need. And I'm saying it's a continuous function. Typically, I'll be thinking about differentiable functions so that I have some nice behavior, but that's what a rigid motion is. Okay, so nothing unexpected. And of course, I just mentioned this, but note that any isometry of the plane gives a rigid motion necessarily. So meaning translations and rotations. And the other thing I want to think about, which is a slightly different thing than a rigid motion. So a rigid motion is really like a function in some local neighborhood of 0, okay? But I also want to think about an infinitesimal version of this. So that'll be like a derivative at time 0. So that's going to be an infinitesimal rigid motion. And of course, as you might imagine, it's much easier to think about because derivatives are easier than actual functions. So here's another definition. An infinitesimal rigid motion so what does that involve? Okay, so if I have a framework like this, what I want an infinitesimal rigid motion to be is essentially a derivative version of this. So meaning that I want to specify a tangent direction at every point. Okay, so that's my desired direction of motion. I'm not actually moving. So maybe I might have some sort of tangent. And before I give the definition, let's just think about it for a moment. I want the rods to not change in length. So every tangent has to be, so let's pretend for the moment that, just for simplicity, that this point and this point are fixed so that I have some like frame of reference. Because of course I can rotate and wiggle the whole thing and that's annoying. But let's fix this green edge just for the sake of convenience. Okay, so this is, meaning that the edges, the endpoints of that edge are not going to have any direction of motion. And now note that if I have this vertex right here, if I want the length of this rod to not change, then its direction of motion has to be orthogonal to the rod, right? So it can be either up here or it can be down there. So I have to choose one. So I have to choose a direction and I have to choose a length. Okay, so that's what an infinitesimal rigid motion is. So that would, in this case, it would be something like, oops, I'm choosing a direction at each of the other points. Now, what about this middle point here, the third vertex of this triangle? What should I do for that? Nothing, because I fixed the green edge and triangles can't move, right? So once I have the lengths of the three sides of a triangle, I've determined everything. So this point here can't move at all. Okay, so this here would be an example, a picture of an infinitesimal rigid motion, and more precisely, what is it? An infinitesimal rigid motion is a choice of velocity vectors one for each point. In general, I won't impose that I'm fixing any edge. Sometimes I might do it for convenience, but in general, that's not part of the definition. So I'm going to choose a velocity vector for each point, but I have to obey the fact that infinitesimally the lengths aren't changing. So this gives me an orthogonality condition. So if I look at any edge, and if I look at, the vector pi minus pj, that has to be orthogonal to the vector vi minus pj. Okay, so this is saying that infinitesimally the lengths aren't changing, and moreover, if you had an actual rigid motion, a differentiable rigid motion, if you differentiated it and evaluated the derivative at time 0, you'd get an infinitesimal rigid motion. So that's also should be not too hard to see. So note that the derivative at time 0 of an actual rigid motion, that's differentiable, of course, is an infinitesimal rigid motion. So, and by the way, okay, so given if you have a rigid motion, you can differentiate it to get an infinitesimal one. You can't always go backwards. So it's a nice exercise to find frameworks that actually have infinitesimal rigid motions, but that you can't integrate. So, so this is like a fun creativity exercise, I guess. Show that or find frameworks that have obviously non-trivial ones, not like the global isometries, right? Have non-trivial infinitesimal rigid motions, but no actual rigid motions. Okay, so good. So what are we doing with this? So as you can see, the framework that I drew here is infinitesimally flexible, meaning it has non-trivial infinitesimal rigid motions. It also has non-trivial rigid motions because you can wiggle the arms around however you like. We've also seen that triangles don't have any non-trivial infinitesimal or otherwise rigid motions. So by the way, if a framework is infinitesimally rigid, then it's rigid, okay? It's not going to have any actual rigid motions. So easy proposition. So, and also, sorry, so my convention is to say that infinitesimally rigid is the same as saying that there are no non-trivial rigid motions. Sorry, infinitesimal. Okay, so one kind of not very difficult proposition that you can write down right away is that if you have a convex arrangement of points and if you triangulate it, it's going to be rigid. Okay, so a triangulation of a convex arrangement of points is infinitesimally rigid. Is this obvious to everyone, or should I say anything about it? Yes. Rotations are global isometry, so they don't count. So, but when I say, yeah, so maybe that this is part of the non-trivial. Pin one edge, yeah. So yeah, maybe I should say that. So non-trivial means modulo rotations and translations. Yeah, so if you think about the space of infinitesimal rigid motions of any framework, that space is always going to have dimension at least 3. It's a vector space, and it's always going to have dimension at least 3 because translations plus rotations gives you 3 dimensions. So translations are 2 dimensions and rotation is 1. So there's always going to be 3 kind of trivial rigid motions, but we ignore this. Okay, so right, so just you can convince yourself of this. It's not too bad. The point is, how do you see this? Well, you fix an edge without loss of generality. You pick your favorite edge, let's say an outside edge, fix it, because otherwise you can always like rotate and translate to bring it to whatever position you want. And then every triangle bordering that is automatically fixed, and then you can kind of keep going through the triangles. Okay, so technically there's some linear algebra to do, but visually it should be clear. So that's good. And then the other proposition, so I'm going to write 2 results, neither of which is obvious to me. I'll give some indication on how to prove them. I may not entirely prove them, but we'll see. So there are 2 propositions. One is that suppose you have any arrangement. So consider any framework. No, I'm sorry. Consider any configuration. Oh, maybe I should say again, sorry, generic configuration. So for the purposes of today's lecture, we're only thinking about generic configurations. Okay, you might ask, I have some configuration of endpoints. I want to start adding some edges to this configuration. So I start off just with endpoints. I start adding edges. If I don't add any edges, obviously the whole thing is flexible. So I can, of course, move the points however I like. There are no constraints. And as I start adding edges, I start adding constraints to my system. And at some point, my framework is going to be rigid. Okay. So the question is, how many edges do I need to add to make a framework infinitesimally rigid? And so the answer, can anyone guess? The minimum number of edges in any infinitesimally rigid framework on these points. It's your favorite number. It's 2n minus 3, as we saw in the triangulations case. So that's great. So triangulations of convex arrangements, not only are they infinitesimally rigid, this proposition proves that if you remove any edge, you get a flex. So you can, maybe you can convince yourself visually of that. Because I mean, if you think about it, if I remove an external edge, then kind of things are easy because I get some dangling bits and I can move them. But if I remove an internal edge, what can I do? And so I get this quadrilateral without any diagonals. And I can you can convince yourself that if you have a quadrilateral, you can kind of flex it. Okay. So again, if you can do some linear algebra also, but visually it's kind of clear. So in triangulations, if you remove any one edge, you get a flexibility. And then, of course, you can add extra edges, but then you get crossing frameworks. Fine. They're still infinitesimally rigid, but this is the minimal number. And then the second proposition, which again, I think not obvious to me, is that if you have any configuration of endpoints, pointed pseudo triangulations are also infinitesimally rigid. Okay, so and it's, I mean, of course, not only is it infinitesimally rigid, it's minimally infinitesimally rigid, right? So this, like, maybe is not completely obvious, but let me again draw an example. Let's look at some examples to convince ourselves that this is actually true. And I don't know how much about the proof I want to say, but we'll see. So let me look at 4 points. Here's a pointed pseudo triangulation. So in any given case, you could probably argue kind of visually, right? You can say, look, here, let me pin this bottom edge, right? And then if I pin this bottom edge, then this entire triangle is pinned. And if this entire triangle is pinned, good, there's also another triangle up here that's also pinned. So the whole thing is pinned. So you can kind of see. And then what happens if I delete any single edge? If I delete this edge, the center thing here is a dangling arm, so I can move it. What happens if I delete one of the external edges? So I'll delete kind of the non-obvious one. So what happens if I delete this edge here? So now maybe, again, not completely obvious what to do, but I claim that this figure has a non-trivial infinitesimal rigid motion. So how can you see that? You have to, so this thing here does have, in fact, a non-trivial rigid motion. And you can kind of say, the motion sort of looks like this. You're like pulling apart. It's like a bellows, right? You're like pulling apart the bellows and then the bottom goes down. So again, you can do this formally with some linear algebra, but I'd rather show some pictures, right? So, right. I'll draw one more example just for fun. Maybe with five points. The nice thing about this is that I can keep drawing edges. I have this maximality business, so I can keep drawing edges up until I get 2n minus 3, as long as I'm not violating any constraints. So here's a pointed pseudo triangulation. So how do I argue that this one is infinitesimally rigid? Let's see if I can do it in an ad hoc way. Well, let me fix this edge. That fixes this entire triangle. Similarly, I fix this entire triangle. And now I have to think about this vertex here. And it's not completely obvious because, like, okay, this vertex I fixed because of a triangle, and this vertex I fixed because of a triangle, but this vertex here is not part of any triangle. So, so you have to kind of do some extra stuff. You can say, oh, like I could add in this edge, and that edge is fixed anyway, and then I get a triangle. So there are some ad hoc arguments that you can make, but of course they don't give you a proof. But the nice thing is that actually these kind frameworks given by PPTs are actually like really infinitesimally rigid. So what do I want to say? Okay, and then I'll say, so maybe I'll indicate how to prove this, but again, briefly, so that we can move on to some representation theory. And the proof is, it's surprising. The proof involves some mathematics from the 1800s. And it's like the bulk of the proof is, so, okay, so how to prove this? Let me back up. Tablets malfunctioning, okay. So the answer is that it's all just linear algebra, but tricky linear algebra, and it goes through this theorem, or I don't even know what to call it, because it's papers from the 1800s, and they don't really like say theorem proof. They kind of give methods or something like that. So it involves the Maxwell-Ramona correspondence. Correspondence, yeah, that's apparently the word. So Maxwell is James Clerk Maxwell. Cremona is Luigi Cremona from the Cremona transform of algebraic geometry. So pretty classical mathematicians, physicists, whatever. And they wrote papers in the 1860s or something, which talk about like some like physicsy properties of frameworks. And so that's what this involves. Surprising. Okay, so let me indicate how to get there. So first, okay, so the first thing we want to do is establish a little bit, like a little bit of technology, I guess, to deal with these infinitesimal rigid motions. So the first thing I'm going to do is I will write down a rigidity map. So now you have a consider framework. Oh, and by the way, my printed type notes will have links to the actual paper, so you can read them. The Cremona paper had to be translated into English. Unless you read Italian, you can read the translation. Consider framework G with vertices P and edges E. And so let's say that the size of P is n, so n vertices, and the size of E is little e. And let's look at the rigidity map. And I guess I'll call it MG. So it's going to be a map. Actually, I'll draw it on the next page. It's going to go from, n points in R2, n vectors in R2, let me say, to like the vector space of all edges generated by the edges, essentially. And what is it going to do? It's encoding the fact that these velocity vectors satisfy certain conditions, one for every edge. Okay. So this map is going to do the following. If I have a vector x here, which I'll think of, and it's a bit funny, but I'm going to think of it as x1 through xn. So each one is also a vector, it's a 2 vector, okay? And this is going to go to the following. So it's going to go to the vector, some big vector indexed by E, indexed by capital E. So in the ijth position where ij is an edge, I simply put this dot product. Okay, so pi minus pj, xi minus xj. Okay, so if you recall, an infinitesimal rigid motion is a collection of n vectors which is killed by this map. Okay, so so note that so an infinitesimal rigid motion is precisely an element of the kernel. Is everyone happy with this? And let me also set up some notation. So as we discussed, so I mean, now from here, it's obvious. If it wasn't obvious to you earlier, it should be clear from here that the space of all infinitesimal rigid motions is a vector space. Okay, and the kernel, we already know it has three things in it. It has the two like translations and one rotation. So traditionally, what people do is people say let the dimension of this kernel. No, yeah, that's right. That's one. Kernel FNG be D plus 3. Okay, so D is the dimension of the space of non-trivial infinitesimal motions. And now, like, okay, on one hand, you have this D. You want to figure out what D is for your fixed framework. So far, I haven't done anything to indicate how to figure this out. So I'm going to introduce something else, which kind of looks really strange at first, but and again, like I'll write down the name and you'll realize, like, it's kind of clear that it comes from the 1800s. I don't know. It's so far so good, nothing mysterious here. Let me introduce a quantity that to me was slightly mysterious. Okay, so I'm going to introduce the following thing. So let me draw a picture first. So I have some framework. And, it has certain edges. And what I want to do is I want to assign a constant to each edge. Okay. And the way to think about this constant is that it's each edge should be imagined as a spring. And this constant is the spring constant of that spring. So now I'm not like super up to date on my physics, but this is what it's supposed to be. So so what's going to happen is that if I have some labeling like this, I'm going to think about constants omega, okay? And now I have to, omega 1, 3. And now, like, these are supposed to be spring constants, so I have to like write down some force balancing diagrams. So this is Maxwell, right? I mean, okay, so definition. And these things, like this assignment of constants, is called a self-stress, okay? So a self-stress of a framework G is an assignment, or I could say a function. Do I want to think of it? Well, let me say an element omega in R to the E. Okay, so they're constants indexed by edges, which satisfies the following equation. So I always mess this up. Let me make sure I'm not, okay, which satisfies the following. So for every, so now like the force balancing equations occur at every vertex. So at each vertex, the forces coming from each of the springs have to balance out. So what does this mean? For every I in P, I have the following equation. So I look at all edges coming out of I, and then write down some sort of force diagram, force equation. I'm not going to attempt to justify in real time why this is true, but I'll let you all convince yourself that this is what it's supposed to be. Okay, but an assignment which satisfies these equations for every vertex is called a self-stress. Okay, but now, like the cool thing, and again, I'm like skipping over some details, but they're details that you can all fill in because you all know linear algebra. It turns out, if you think about, so now, if you think about self-stresses, self-stress is also a form of vector space. It's not too hard to see because you can add self-stresses and you can multiply them by scalars, fine. Not only do they form a vector space, now here's a little bit of like orthogonal linear algebra that you have to do. In fact, omega is a self-stress if and only if omega lies in the image of mg. So this is an exercise. Not too hard, but. So mg was this rigidity matrix, okay? And it's, if you have something in the image, it's not too hard to see that it gives you a self-stress, but the converse is also true. Great. And am I saying the right thing? Yeah, I think that's okay. And now, once you have this, so now let S be the dimension of the space of self-stresses. Now you do a little bit of like rank nullity on the whole thing, okay? And you conclude the following, okay? So, so again, easy, but sort of not, I find it difficult to do in real time. So what do I want to do? Okay, so the rank of, no, what do I want to do? Dimension of the kernel plus dimension of the image, right? So I'm just going to write the equation. This is hard to do in real time, sorry. So, so if we have, so again, remember that mg is a map that goes from R2 to the n to R. Is there a comment? Okay. And so what do we have? We have that the dimension of the kernel of mg is d plus 3. The dimension of the image of mg is maybe up to a transpose or something, but is S, okay? And E is the number of edges, N is the number of points. I claim that you can conclude from all of this, if you think a moment longer and if you're not standing in front of the room, is the following. So all of this implies that on one hand, E equals, no, not on one hand, E equals 2n minus d plus 3 plus S. Okay, so this is again not to, it's pure linear algebra, which I can't do in front of the classroom. So this is once again an exercise. But let's see what this means. Okay, so this is E is 2n minus, and again, let me rearrange so that I have my lovely number 2n minus 3 here. So E is 2n minus 3 plus S minus D. So it's saying, here's a framework. It has D non-trivial infinitesimal rigid motions. It has S many self-stresses. And the equation that it must satisfy is the following. So now, if you think about it, if a framework is infinite, so let's just stare at this equation for a minute. If a framework is infinitesimally rigid, that's the same thing as saying that D is 0. S is the dimension of something. It has to be non-negative. Okay, so this immediately implies that if a framework is infinitesimally rigid, then the minimum number of edges that it needs to have is 2n minus 3. So this proves the minimality or whatever proposition. Okay, so this implies if D equals 0, then E has to be bigger than or equal to 2n minus 3. Okay, so anything with fewer edges than that is bad. It doesn't yet tell you anything about pointed pseudo triangulations, because like, how do you compute S? Is that a question?
I'm just not seeing where we get any equation. Like, are we just
Oh, E is I think you're computing, so the equation you get is by writing down two formulas for the rank of the matrix MG. So you can either compute the rank using the source and the kernel, or like using the image and the codomain. That's where the E is coming from. Yeah. Yeah, so this is, exercise, write down 2 formulas for the rank of MG. Yeah, as I said, like elementary linear algebra, but somehow not trivial. Okay. Okay, any other questions? So now, the nice thing is that like computing D for any fixed framework is maybe like not trivial to do. On the other hand, this equation reduces the calculation to computing the space of self-stresses, which again is not clear how to do that, but that's where the Maxwell-Ramona correspondence comes in. Okay, so this is something I'm not going to talk about in too much detail, just because like it derails from the direction in which we're going. But just for fun, I want to mention it because it's from the 1800s. Like, how often do you get to use a paper from the 1800s? So proposition. So not proposition. I mean like a claim. Okay. So first of all, okay. So this tells you that computing D reduces for a fixed framework. Let's say reduces to computing S. Okay, and the claim, and all of this is written in the notes, so you're welcome to read it. The claim is the following, and do I want to say, okay, so the claim is that S can be computed for a given framework, and indeed for like a pointed pseudo triangulation using this thing that I had mentioned, the Maxwell-Ramona correspondence. And I'll give you a 2-minute summary of this. And this, yeah, again, like this is something that is really not obvious, but somehow ends up working out. So what you do is the following. Okay, so if you have a framework, so this is not like a formal proof or anything. It's simply some pictures which tell you what to do. Okay, so if you have a framework like this, you want to compute its self-stresses. Okay. It turns out that you can relate the calculation of the space of self-stresses to another vector space, which is called the vector space of Maxwell liftings of this diagram. Okay. So what's a Maxwell lifting? So instead, so this is like C notes for details, but so if you have a framework, you can look at its Maxwell liftings. And what's a Maxwell lifting? Well, you're supposed to, I mean, maybe like technically you want to impose some other conditions, but so let me focus on like a triangulation or a pseudo triangulation or something, just to make my life a bit easier so that I don't have dangling edges. It doesn't really matter. But what's a Maxwell lifting? I want to, first of all, like pin down all of the outside edges. And then for every inside edge, I want to give a height function. Okay, so you should imagine like I have my framework in a plane like this, and my z-axis is upwards. And a lifting is something where I like pin all of the edges, vertices on the like outside, and on the inside, I kind of like pick up and lift the vertices. And of course, as I do this, every face has to remain planar. Okay, so I have to give some like height function for each vertex so that each face remains planar. Okay. So roughly speaking, each internal, and maybe some internal vertices may have lift 0, but fine, some height. Okay, so lift each internal vertex so that every face remains planar. And And when you do this, is there a question? Somebody? No, okay. And when you do this, okay, sorry, I don't know what they're saying, but when you do this, it turns out that the theorem of Maxwell and Ramona is that the space of self-stresses, so S, I guess, has the same dimension as the space of Maxwell liftings. So it's this crazy, like, physicsy thing that you have to do. But now, apparently, like for pointed pseudo triangulations, if you really think about computing Maxwell liftings, you can compute them and see that you don't have any. Hawaii, are you saying something? I can't hear you at all.
The room is silent, I think.
Yes, this room here is very silent, so I don't know where you're.
Okay,
here.
I don't know what's going on. Sorry about that. Okay, so it turns out that the space of self-stresses is the same as the space of Maxwell liftings. And so like using this crazy detour through like some lifting business, you can actually compute the space of Maxwell liftings for a pointed pseudo triangulation. And for a pointed pseudo triangulation, it turns out that there are no Maxwell liftings. And fine, and that tells you that there are no self-stresses, that tells you that there are no infinitesimal rigid motion. So it's kind of interesting. Okay. So that's what this all says. But I'll leave it at that. Yeah. Yeah. So in this framework, it's kind of obvious, but I could draw a more complicated framework where it's not obvious. Yeah, of course, this framework has triangular faces. So what does that even mean? But here's a. So this thing here is a face, and that has to remain planar, and that's not guaranteed by anything. Right? But now you can see why this thing doesn't have any Maxwell liftings. Also, because like if you try to lift the central vertex while pinning these three vertices, then this face won't remain planar. So that's that's basically, you can extend this argument to an actual proof. Okay, excellent. So the last thing I want to say about rigidity is, as a consequence of all of this, you can also prove that a pointed pseudo triangulation with an external edge removed has exactly 1 degree of freedom, meaning exactly one non-trivial infinitesimal rigid motion. Okay, so I already drew examples of this. So I'll draw 2 examples again, just to have something to look at. Okay, so something like this. Or you may have something like this. Okay, so in each case, as you can see, like there's basically one thing you can do. But there's more to this proposition, which is super useful. And this is a theorem of Stringing. Actually, this proposition may also be due to Stringing, I'm not sure. So not only is it the case that it has one non-trivial infinitesimal rigid motion, but if you think about it, like the rigid motions that this kind of framework has, a PPT minus an outside edge, the motion kind of expands all the distances. It's not only is it like an infinitesimally rigid thing, but it's not contracting any distance. So this is super powerful. Moreover, so an add-on to the previous proposition, the unique motion, so actually there are 2 add-ons. is expansive in one direction. So you can make this precise. I mean, it infinitesimally increases all distances, meaning the dot products are positive, okay? And 2 can actually be integrated to an actual rigid motion. So I won't discuss the proof of this. This is kind of tricky. Okay, so no matter what configuration like this you take, you get an expansive motion, and it's not just an infinitesimal motion. You actually can integrate it to an actual motion. Okay, so I guess we won't get to like, okay, we have, is it 11? Oh, I'm supposed to stop at 11:50. Okay, so I'm supposed to stop now. So I'll just say go back. So I was supposed to explain 2 appearances of PPTs. I have explained one of them, but the second one I will get to tomorrow. And before I get to the second thing tomorrow, I also want to explain, like in 5 minutes, why Stranu was thinking about all of this stuff, like what is an application of this nonsense. Yeah, I'll talk about that tomorrow. Okay, thanks. Yes. The example on the left, the question was, why does the example on the left have a Maxwell lifting? The answer is it does not. It doesn't have a Maxwell lifting, but let's go back up. So you're totally right. Let's look at this equation here. You're right. The example that I drew, a PPT minus an edge, like the arrow shape, doesn't have a Maxwell lifting. So it doesn't have any self stresses, but S is 0. Okay, but E is not 2n minus 3, it's 2n minus 4. So that adds a D. Does that make sense? Yeah. So it's you're also missing an edge. So that means you pick up a D. Other questions?
Yes? How do you...
Oh, sorry, Hawaii. Can I pause you for 1 minute? There was just a question here. The question was, if you do a Maxwell lifting, do you have to keep all of the edges the same length? No, because when you lift, the kind of like, yeah, the lifting involves an increase in the length. Hawaii?
How do you view the set of Maxwell liftings as a vector space?
How do you view the set of Maxwell liftings as a vector space? Good question, but I guess it's so okay. So I think you just have to check directly that you can add 2 Maxwell liftings and you get a third one. I don't know if I have a better answer than that, but if you have a Maxwell lifting, one Maxwell lifting that keeps each face planar, and then another one that still keeps each face planar, you have to convince yourself that if you add them, you still get a lift that keeps each face planar.
Okay.
It's probably more clear when you kind of like actually try to prove the whole thing, but at the moment I don't have a better answer than like imagine it or something. But you can write down some linear equations and then it becomes clear.
Okay, thanks.
Other questions? Okay.
No more questions. Let's thank the speaker again.